Okay, so I think we talked about, and I didn't get to explain the notation correctly. First of all, remember, we have combined space and time. This, for example, is x0, and this is x3. So you have x1, x2, x3, and x0. And we talked about time translation, we talked about space translation, we talked about rotation and Lorentz transformation. So to write all of this in a compact way, I can write a transformation to be of this type. And I realized that I had to define things and you were confused about what this object was. So this is a matrix. It's a 4x4 matrix. So for example, this matrix is lambda 0, 1, lambda 0, 2, nope, lambda 0, 0, lambda 0, 1, lambda 0, 2, and lambda 0, 3. What is this guy?
Lambda 1, 0.
1, 0. This would be lambda 1, 3. This would be lambda 3. This would be lambda 3, 0. Yeah? And
Wait, what about?
Oh, there's stuff here, right? Let's just write it down. Okay.
I see.
Yeah. I mean, there are 16 elements. A mu is just 4 numbers: A0, A1, A2, A3. So these are typically called 4. Well, I'll get there shortly. So for example, if I pick lambda to be 0, and if lambda equals 0 and a mu equals A0, 0, 0, 0, what kind of a transformation is this? Oh, lambda cannot be 0. Lambda
0 matrix be 0, 0 mu.
Intended. What kind of a transformation is this?
Just a time-based transformation?
Say, almost, correct?
Space-time transformation, or time transformation?
Time translation.
Time translation.
The whole Eastern versus Central time. Is that clear to you? What if this continues to be true and we had spatial translation? Yeah? Okay, what happens if A mu is 0 and lambda is of the form? What form will it take for Lorentz transformation about the x-axis? Well, for one thing, y and z is not affected, right? What should this be? Here, let me help you. X bar equals gamma x minus vt, or I can put beta times ct. And t bar, c bar t bar equals gamma c bar t minus beta beta x. Is that correct, guys? Take a look. So, if this has to be a Lorentz transformation, obviously A has to be 0. What should this be? I've made it almost clear. Can you tell me what it should be?
It just have to be identity matrix, right?
No. Then what we then x bar mu equals x mu.
Okay.
That's no transformation at all. What would the Lorentz, how can I write this as a Lorentz, what matrix do I need to pick so that
Gamma?
this is a Lorentz transformation?
What about gamma?
I'm sorry?
Gamma?
Where?
On the diagonal, on those two spots.
Well, let's do it one at a time. Tell me what goes here.
That one should be gamma times 1 minus beta x.
What should be, I'm making it confusing, you know that, don't you?
Okay.
This is just matrix multiplication. Right? If A is 0, that's what this means. And you see the transformation there. What should it be?
Gamma times 1 minus beta x over ct.
Not quite. What should this be? I'm going to make one more. Second guy. What is the first guy?
Oh, is the first guy just gamma?
Just gamma.
I see.
All right. So what's the next guy?
This guy will be. This one will be beta first and then gamma.
No. Beta first and gamma is all good. What am I missing?
Oh, beta gamma. Sorry. It'd be beta gamma and then gamma. And a negative. Sorry, it'd be negative beta gamma. And then,
Negative beta gamma.
yeah.
Everyone agree? Don't agree too fast because none of you spoke up. Is it clear? Ask. What's going on, guys?
How did we get there?
Thank you.
Well, it's just matrix multiplication to yield those Lorentz transformations.
Yeah, so this guy is this product. So I would have gamma CT, look, gamma CT. Then I would have minus beta gamma X, minus beta gamma X.
Okay.
Yeah. And lambda is just our transformation matrix, right? That is the idea.
Lambda is it's a compact way of writing Lorentz transformation and rotation.
Okay.
If I want this to be a pure rotation, let's make it easy, about the z-axis, okay? For rotation about z-axis. Now, okay. Tell me the first row. Let me make sure this is.
Is it just for the rotation of the axis?
It's just rotation about the
So
z-axis.
no Lorentz transformation here.
No Lorentz transformation.
Okay, so it'll be, first row will be 0.
Huh?
Completely 0, right?
You're gonna be 0,
Or, sorry, 1, 0, 0, 0.
1, 0, 0.
Yeah.
1, 0.
This is time. First row is time. Yeah.
Now what?
Your second row is going to be 0, then you have cosine theta.
Cosine
and then-
phi.
Sorry, cosine phi, sine phi.
Is it sine or minus sine?
It's positive sine if you're just doing about the z-axis, it's positive sine.
Are you sure?
Minus sine down the bottom left, yeah. I'm
I
fairly
believe
sure.
you.
I'm fairly certain. I might be wrong.
Yeah.
Yeah. It'll be sine there and.
Should I believe you?
No. I mean, always double check, but.
It's Jackson, I believe.
Me too, at this point. Always confirm before you.
Yeah, it's a good idea to confirm, but yes.
Good, so I think you guys have a hang of
Angle
it.
sine 3, and then 1 in the bottom right. That's it.
So now you see what that notation does, right? It is a compact way of writing, and now you can see if it is a purely rotation matrix, this might get complicated. It'll be a 3 by 3 matrix that'll get complicated. Similarly, if you're doing Lorentz transformation about an arbitrary axis, well, then this is a mess to write. But it is a matrix. These are linear transformations. Yeah?
Is it
Okay.
Just by chance that the Lorentz transformation looks identical to the rotation, just that
Yeah.
it just
They are
they're very similar. It's just that there's like the
that extra minus sign,
yeah, the
right?
extra minus sign.
We'll talk about that. It's like sinh and cosh.
Okay.
Yeah. Because cosine squared plus sine squared is 1. Here it's cosine squared, I don't know which way, cosh squared minus sin squared is 1, or the other way around.
Maybe.
Yeah.
I don't.
Well, it's one or the
been a
other.
while since I've talked about
Yeah, one or the other.
hyperbolics, but-
Yeah, time is just negative of space. We'll get there, right? That's only statement I make, that's not true. But we'll clarify what I mean by that. Okay, so now I want to distinguish between points in space-time versus a vector in space-time. Now clearly, I can only draw in this 3D perspective. Normally, if you were taking E&M, I could draw the XYZ axis, but I can't do that here because this is reserved for what? CT. So it's X and Y. Maybe there's Z somewhere. It goes into a different dimension. You don't see it in this diagram. But so if I look at this point over here, it has some coordinates x mu. That we won't refer to this as as a vector. Okay? It is just a point in your space-time. You could even say it's an event in your space-time. Something of interest is happening there. But for it to form a vector, it must have, in some sense, intuitive sense, a vector at this point should look like this. Correct?
It has to be
So-
forward in time.
I'm sorry?
It has to be forward in time.
No, I don't mean that. I mean any vector. I could even make it parallel to the x-axis. Yeah, a vector has to have an origin and an arrow, and this arrow will have a certain length.
Is it just that conceptually it goes backwards in time in that case?
Forget about where it's going in time, and we haven't talked about anything. It could be a tachyon that can go backwards in
It's
time.
just a vector and like
Yeah.
normalizes when it goes to 0, 0.
Yeah.
Okay.
So it's just at any point you have a vector. So these guys, the x mu, so x mu, locate position in spacetime. But however, delta x mu is a vector. Because I'm just going to pick a nice looking vector. The delta x mu, when I say delta x mu, what do I mean? x2 mu minus x1 mu, correct? So in that case, this could be, for example, x1 mu, and this could be x2 mu. It is a vector located at this point. It's a vector located at x1 mu, and if you will, pointing towards what? X2 mu. That is a vector. So how do vectors transform? Vectors don't care about Eastern Standard Time because vectors is physical, right? So they don't care about Eastern Standard Time or whether you're measuring distance from Troy or from New York. So transformation property. Of a vector. Delta x bar mu equals lambda mu. Oh, let's not forget the Einstein summation convention. I talked about it. Is that clear in your head? When you see this, what's being summed?
into X, right? Like,
New.
yeah.
New.
It's over.
New and new is going to be, yeah, repeated indices up and down. So this is delta x new. Well, I'm going to write this next term and then I'm going to erase it. What's the change in a constant vector?
0.
0. So this is 0. And well, let me just write it. I don't know what state I defined it, but I may want to say it like now. Yeah, let me just say it now. Any object that obeys the above transformation property is referred. How many R's in referred? Referred to as a vector.
I have a question.
Huh.
What is A? We've put it in that equation, but I still don't quite understand why it's there.
A is any four tuple, as I call them, because they are responsible for time translation and space translation. So suppose you don't have any Lorentz transformation or rotation, this just becomes identity matrix.
Okay, so it just
And
becomes xv plus whatever you're okay. So
Wherever you're translating
gotcha.
to.
So
Yeah.
if you're doing like a Lorentz transformation and you're not necessarily doing any spatial translation or temporal translation,
This will be 0.
that'll be 0.
Right.
Gotcha.
Conversely,
Okay.
if you're only doing a space or time let's just stop saying it with a space in between, no pun intended. If you're doing a space-time transformation, this is identity, and
that's
this,
gonna be unknown.
that's what it is.
Yeah.
But look at what vectors do. They don't see translations.
Makes sense.
A vector is a physical object, right? Yeah.
Will we do both at some point?
Yes, so we will do this, but in principle we can. And the more you want to delve into the mathematics of it, we can. In practice, not so much. Yeah. So yeah, this is how points in space-time transform. This is how vectors transform. Now, this is one kind of vector. This is sort of a vector that points from one position to another position, but you can have different vectors. For example, velocity is a vector. This looks almost like velocity, you have to divide by time. But no, forget that. The electromagnetic potential is a vector, right? So there are many, many vectors. So they won't all be delta x. So a vector is any, in general, a vector at the point x mu is denoted as x mu of this x. Oh, y, it doesn't matter. Y mu x, you a mu of x. It's at the location x, these are the components. Yeah? But why would they be a vector? Because under a generalized space-time translation and Lorentz transformation, how do they transform? Only by this guy. It is just blind to space-time translation. Okay. Now I want to transition to space-time metric. So let's do a simple result. So equation 2.3, which is precisely what I just erased. So equation 2.3 is x bar mu equals lambda mu x nu plus. So this is 2.3. So the problem, or I call it a theorem, under 2.3. So when this is happening, what am I claiming? Yeah, this quantity. It does not change. Under Lorentz transformation, this combination does not change. Unfortunately, being very grand, I call it a theorem and not a problem. If it were a problem, it would be your problem. So now it's my problem. Yes?
Why do we call it delta CT instead of just delta, or C delta T?
Oh, yeah.
Well, I mean, like,
C is CT is the coordinate.
Yeah,
Yeah, it is.
it's technically C delta T, but
It is C delta T.
I mean, like you could write it either way, but why would we choose
Because
to
my
write it?
x0 coordinate is CT.
Okay, so you just, I see. That's
Yeah,
right.
yeah.
Gotcha.
It's the delta of the x0 coordinate. Yeah? So, yeah, that's just a quirk. It's not. So first of all, it's easy to show. What does it mean? This means the following. I'm going to start with barred quantities. And for now, I'm only restricting to translations, rotations, and Lorentz transformation in the x-axis, okay? We will do the general case as a beautiful, beautiful result pretty soon. But what would be my goal? I'm going to start with this and insert what the other objects are, and I should end up with, this should be equal to what? If this guy's an invariant quantity, this should end up being equal to that. I don't need to worry about translations, do I? Because when I do delta, what happens to the translation?
It's a vector, so the translation
It goes away. Do I need to worry about rotation?
Yes.
I do? Well, what does rotation preserve? If it is a pure rotation, it preserves the length of x, y, and z. Isn't this the length squared? So the length squared is preserved, and in rotation, time is not even affected. I don't have to worry about rotation. The only thing I have to worry about, for now, is boost along the x-axis. And so let me just plug it in. So this is equal to, I have it written in my notes, so I'm just going to move along very quickly. There's a squared here, so I get minus gamma squared delta CT. I'm just putting the Lorentz transformation in, minus delta x squared plus gamma squared delta x minus beta delta CT squared plus delta y squared plus delta z squared. First of all, is this correct?
Yes.
That is correct. I said I don't have any faith in you, Jackson, but do you have faith in me?
I do.
Well,
Usually.
don't.
Usually.
I would like for you to, this is just algebra, right? If you spread it out, guess what's going to happen? This becomes precisely that. It's not so trivial. Remember, there's a gamma here. There's a beta here. How are gamma and beta? So let me write the result. You can verify, and please do verify. Sometimes even if it's just simple algebra, you have to go through it, right? And this ends up being minus c delta x squared plus delta y squared plus delta z squared. You you have to verify this. Because gamma, or I can say gamma squared, is really 1 minus beta squared. So when you collect all the factors, next to every gamma squared, there'll be a 1 minus beta squared. So you can get it to be. So please verify. There's nothing deep going on, but it is important to verify.
I feel like just
Huh.
very quickly you could just like look at it and it would verify because you have gamma squared times delta x, gamma squared times negative beta delta x, and how much cancel out.
If you squint, you'll see it.
Yeah. It's already pretty sure.
It's if you want to see the Andromeda galaxy on a dark night with your naked eye, what do you do?
Squint.
Look away from it. That was a trick question. Your peripheral vision is better than your direct vision, so you can see that. That may be a trick that you choose to believe in. I don't know. I tried it. I squinted. I looked away. Nothing. This is what I've been told by professional astronomers. Veronica, you should verify this, right? As a future astronomy person.
The Andromeda thing?
Yeah. Have you seen it?
Yeah, you squint.
With your naked eye?
Yeah.
You squint and you saw it?
Yeah. You have to like block out the rest. You squint and put your hands around your eyes. And
Well, maybe it's squinting. I thought it was looking away.
Well, looking. I mean, they
I
could
mean,
probably
it
either
works.
work.
Either way it works.
Yeah.
Well, there's something weird with the light falls in your eyes. If it hits it at an angle, it actually is really stronger.
Blocking the light around you makes it less exposed as well.
So it's
It's either
makes it
or,
better.
yeah.
Or better.
And both.
Okay, so now, so first of all, notice it's this combination that is invariant to relativity. This is what I mean by space is negative of time and vice versa, right? It's not a precise statement, but if you look at the invariant quantity,
Literally
yes,
is.
right, yeah. If you look at the invariant quantity, it almost looked like a dot product in 4 dimensions, except the time component has a negative. So now as homework, again, I described the homework problem so you can see its importance. This is problem 2.4. So you will see why you want to bother showing the result. Suppose you have 2 vectors, x mu and y mu. What I want you to show is minus of x0, y0, plus x1, y1, plus x2, y2, plus x3, y3 is also invariant. Here, it's like the same vector. You're taking a vector and dotting it with itself. Correct? But here, it's just any 2 vectors. This will be invariant. And at the moment, for you today, what are the transformations that you should look at? Space-time translation, rotation, and Lorentz transformation. We're not doing anything else. Listen, space-time transformation is not affected by vectors. Rotation, this is the dot product of spatial rotation.
Which will
That is not affected by rotation. All you have to make sure is under Lorentz transformation, it is invariant. It is really a small, tiny variation of this. But nonetheless, this looks like a space-time dot product.
So would you just Lorentz transform x and y?
X0 and Y0, X1 and Y1.
Okay.
According to, what you'll do is really you'll start with minus X bar 0, Y bar 0, plus X bar 1, Y bar 1. These guys
And then you show that those through the Lorentz transformation stuff that we did over there would still end up being
will still end up being this.
equal to that.
Yeah.
Okay.
So what that tells you is, it's not called a dot product, but it's effectively that sort of an object. The dot product or the inner product in this 4-dimensional space-time is almost like you're